electronic packaging. We're going to go over surface mount technology and soldering and stuff when we get to that. So I decided I'd go ahead and start today on adhesive bonding. A lot of people like to start talking scientifically about adhesive bonding in terms of the Leonard-Jones potential. I don't know if I didn't make a copy of that for today. But the Leonard-Jones potential basically is the force of attraction of two atoms. We talked about it before. This is the energy between an atom. You've got an atom right here, and if you have another atom at some distance r away, and that other atom is brought closer and closer, it will finally find some equilibrium distance of separation, typically called A0. Not necessarily lattice spacing, but sometimes in a simple cubic cell it's a lattice spacing. In any case, people like to talk about the bonding of the atoms as they get close together. And in fact, I like to bring this book in called Fundamentals of Adhesion, and it's edited. It has some of the authors in here are Nobel laureates and things like that. But this first chapter talks about the four forces of nature. And it talks about gluons and adhesion of nuclei, okay? The nuclear equation of state, okay? We're talking about how protons and neutrons get together. I mean, you know, in terms of a practical sense, this was, the editor of this was at a large firm research lab in Rochester, New York. They'll remain nameless, but their name begins with X and ends with X. And they worry about how to stick little particles on pieces of paper. But, you know, they've gone back, adhesion is their business. But, you know, how many people are really gluing protons and neutrons together? And so the real value of a book like this is sort of like that, you know. Actually, there are some good parts of the book. And I have to use it next year. So I will retrieve it. But it's sort of garbage, is my point, in a practical sense, to start talking about adhesion between two iron atoms, although that's what I did on the second day of class. I started talking about the forces of adhesion. If you can get two iron atoms or two aluminum atoms together, the primary bonds are extremely strong. However, when we start talking adhesive bonding, you never get that stuff together. Remember I said there are two problems, surface roughness and surface contamination. And every process we're going to talk about, except adhesive bonding, does something to remove the surface contamination. Adhesive bonding is the only process we're really going to talk about where all we do is bury the contamination underneath some glue. We don't get rid of the oxides on the surface in adhesive bonding. We don't always even get rid of the moisture that's on the surface, or some oils and greases. We might get rid of them in some adhesives because the adhesives will tend to dissolve them, and you get down to the oxide layer. But you're not bonding to a metal surface. You're certainly not bonding to protons, which is why I threw the book in the trash, right, to make the point. Why do I need to step back that far to look at the fundamentals? And so my approach to adhesive bonding is somewhat more practical, and you will find some of it in the literature. It's actually not initially my approach. There are a couple of books, one of which was written by an MIT civil engineering professor. What could be more practical than civil engineering? However, he wrote it in 1961. However, it's still one of the only things that I know of that talks about the Teflon equation. It's called The Science of Adhesive Joints by Bickerman. And another one, I still prefer the second edition. This is the third edition. It's just Handbook of Adhesives. The reason I prefer the second edition is there's a chapter, and I've handed out this chapter to you, chapter 3 by Eastman. Eastman was a scientist at the Naval Research Lab and studied adhesion for his career. Eastman's retired, so he didn't make it into the third edition. But actually, this particular plot comes out of Eastman, and we're going to do a little experiment here in a second. But basically, I like to break down adhesive bonding into, and this is a Tom Eager approach, type 1, which is adhesion caused by the of a liquid interposed between the surfaces, okay, of two materials. So in type 1 adhesive bonding, I essentially have an adherent, which is the solid. Actually, I have two of them. And I have a liquid adhesive that has to wet the surface. So I'm not going to start at gluons holding neutrons and protons and, you know, together and the nuclear forces. I'm going to start with surface energy. And surface energy is essentially unsatisfied bonds. We're still talking bonds, but we're talking van der Waals bonds. We're not talking primary bonds. We're not talking nuclear bonds. We're starting with a macroscopic view of van der Waals bonds, which is basically surface tension. Okay, we're not even getting rid of the oxides. If I was talking about a ultra clean metal surface with no oxygen on it, you might be talking a primary bond between oxygen and the metal. But we're talking about an oxide surface, and we're really going to be talking about van der Waals bonding. Now remember, van der Waals bonding with an energy of 1/10 to 2/10 of an electron volt per atom potentially has the strength capability of 100,000 pounds per square inch. We don't always get that with adhesive bonding. As we know, in most bonding, we only get about 1/10 of the potential chemical bond strength. But if I have a liquid that wets this surface, it will flow between the surface, and it will actually tend to pull these two surfaces together. If I have a little bit of liquid, if I have a lot of liquid, the stuff just kind of falls apart. But if I had a bunch of balls sitting on the table here, and I put a little bit of liquid on there, and the balls actually, the liquid wet the balls, it actually would pull the balls into the center and hold them by surface tension, pull them together. And the way it does it is basically, if I have a thickness D and I have a diameter, if these are two discs, simple discs, 2R, then it turns out there's a pressure differential. Let me redraw this quickly. There's a pressure differential between here, out here, which is the ambient pressure, and the pressure in here. And the pressure is given by, or the difference in pressure is given by the surface tension times the curvature, which often is kappa. So that's surface tension, and kappa is the curvature of the surface of the liquid. And so P in the liquid minus P ambient equals gamma of, in this case, the liquid vapor interface, this surface here, because that's one of the, this is the curvature right here, right? And if this distance is D, and that is, if that were a semicircle, then that curvature would be D over 2, right? So that would be, or if you want to call that R, it actually is R. The curvature is 1 over R, well, let me write it over here. The curvature in general of any surface is 1 over R1 plus 1 over R2, where R1 and R2 are the two principal radii of curvature of the surface. So for a sphere, R1 is equal to R2, and the curvature is 2 over R. And so it turns out the pressure differential inside a spherical balloon or a spherical bubble is 2 gamma over R, right? Because it's just gamma times the curvature. In this case, it's 1 over big R, capital R, which is this R, and then it's this little r. But that little r, the curvature here, we're defining the curvature from the center point of this thing. It's that little r is negative in terms of the center point. And so it's 1 over big R minus 1 over little r is the curvature of that surface. This is a saddle point, if you will. It's circular this way, and it's circular this way. It has a saddle shape. And so it's 1 over r minus 1 little over 1 over little r. Well, if big R is a lot larger than little r, it goes to 0, and there is a negative pressure inside here, tends to pull these things together. Okay? Now, if these were two spheres and I put a liquid between them, it would suck them together. Okay? So, how do we prove that? How do I prove it to you? Well, anybody know what Johansen blocks are? Gauge blocks? Sometimes Weber blocks is also called Weber blocks. If I was a machinist and I wanted to make something very, very precise, for example, since some of you are in the Navy has Seahawk helicopters. No, they do have Seahawks. That's made by Sikorsky. But they also have MH-53 Sea Dragons, okay? Big, powerful, yep, okay? And they got a 40-inch diameter bearing on top of that thing. Unfortunately, some of these have failed and killed a few people. But in recent times, and the Navy spent millions and millions just replacing all the bearings in the fleet. It's not the bearings' fault, it's Sikorsky's fault because they screw up the design of the swash plate, but they don't tell the Navy that. The Navy's starting to figure it out, though. Down at Cherry Point, those people are starting to figure out Sikorsky. The latest JAG report basically blamed it on Sikorsky, but for the first 5 years they were blaming it on the bearing manufacturer because that's who Sikorsky was pointing the finger to. But anyway, Sikorsky did all kinds of great things, like the machine tool that they used to machine the swash plates, they destroyed. Didn't bother to tell anybody, they just went out and destroyed it. We know it was machining it improperly, okay? But so the bearings were being squeezed to death by the swash plate, but anyway. But it turns out in that 40-inch diameter bearing, you have to maintain a tolerance of plus or minus 0.02 of an inch on the diameter, okay, to get the clearance for the balls and everything else. Actually, it may be 4,000. It must be plus or minus 0.02. But it's roughly 1 human hair over 40 inches. Well, 1 human hair over 40 inches, if you change the temperature of your room by 5 degrees Fahrenheit, you are going to screw up that measurement. In fact, the way they make that measurement in the field, or in the shop where they're machining this thing, they actually take the caliper, the 40-inch caliper, which is just a long rod with a micrometer, basically, that screws. They put it into the machine tool and flow the oil that's flowing over the part right over it. So it's exactly the same temperature. The oil's flushing the part, and it's flushing the caliper tool at the same time, so that when the machinist goes in there to measure it, everything's at the same temperature, okay? So it's a really, really, well, it's really, really precise. Well, if I want to get things really, really precise, it turns out I need to have some sort of standard to measure my length. And I can buy a whole set of Johansen blocks, which are basically, this is a 3-inch long Johansen block. It has ground surface, it's actually ground on all the surfaces. This one actually is chromium carbide, so it won't wear and it won't rust. Like originally I bought some steel ones. There's a 2-inch Weber block, but they rust if they're just made out of hardened steel. And if you get a little rust on there, they're not precise anymore. This is precise to 50 millionths of an inch at 72 degrees. And in fact, it's got a certification standard that goes with it. Well, it turns out to keep these from rusting, you basically, and this is not the bound surface, you can slide them together, and all they got is a little bit of light oil on them. The light oil is the adhesive, and it actually takes some force to separate them. But the better way, which I haven't done yet, the way a machinist actually do it, he's interested in putting 2 3-inch ones together, let's say, to make 6 inches. Oops, I'm feeling some dirt. If they get the least little nick on them, or aren't very, very clean, or they don't have the right kind of grease, okay, that's good. It's called wringing them together, and it turns out I may need a little bit of lube. It may need a little adhesive. If you get too much, it's don't usually have this much problem with it. There we go. Okay, so you can wring them together, and all I got, well, you can tell they will slowly pull apart because the oil has some viscosity and it pulls apart, but and we're actually going to go through the equation for that. But there you have a light oil, which is the adhesive. Now these actually, it's easier to do it this way, where I have more grease built up, and I'll pass them around. Yeah. If you really wring them together well, they will stay together for a considerable period of time if you get the right amount of grease. But unfortunately, anyway, if you want to try to play with them, you can. Oh, those are sticking pretty well. It's just getting. Okay, there you go. So they should do better than the bigger ones, but okay. Okay, so that's type 1 adhesive bonding, or what I call type 1 adhesive bonding, and it's just because I've got a liquid between two solids. And it turns out that you can write down some equations for this type of bonding, and one is called the Stefan equation, and the Stefan equation is worked out in Bickerman in some detail. He goes over several chapters of working out the Stefan equation in lots of detail. But the Stefan equation basically assumes that I have a viscous liquid between two plates. Oops, I better get it over here so you can see it. A viscous liquid between two plates, and in this case, he actually solved it for spreading of drop under pressure. This is the same Stefan as Stefan Boltzmann, and the Stefan solved this thing originally. And he just was worried about a viscous liquid between two plates and how it spreads out. Well, it turns out it doesn't matter whether you're squeezing down or whether you're pulling up. The basic differential equation works the same in either way. And you can actually, I'm not going to solve this differential equation. You can go to the Bickerman's book if you want to solve the differential equation. It's not that hard. But the final equation is as follows, basically. The force time product for pulling those gauge blocks apart, if they were a circular disc of radius A, is 3/4 pi. Eta is the viscosity of the liquid. A to the fourth, 1 over h2 squared minus 1 over h1 squared. You're going to want that equation, although I think it's in your notes somewhere. But in any case, you'll need it for several homework problems. Well, you notice that as I held it, in a little bit of time, it fell off. And in fact, I actually call this is sort of the Scotch tape equation. In fact, I sometimes call this the Scotch tape lecture. If I were to put something up on the wall with Scotch tape, and it hangs up there for 15 minutes, then it just kind of falls off the wall because the Scotch, it didn't have very good adhesion. Well, what do? Typically, I pick it up and I put it on the wall and I rub it a lot harder, right? I just put it on with more force, right? Well, all I'm doing in that case, according to the Stefan equation, oops, this thing slipped on me, okay. According to this Stefan equation, 22, okay, not a very good focus, is it? You never know. Can't get much better focus when you blow it up too much. According to the Stefan equation, H2 is the original height and H1 is the final height. So if H2 is much larger, then I'm going to get a negative force, a force of attraction, if H1 is very small. Okay? So when I apply more force in putting it down, I'm trying to get a very thin layer. And why I want a very thin layer? Because when it then has a lower force, just the hanging weight force, trying to pull it off, it's going to take longer, because this is the force time product, to pull away if I start with a very thin gap. And it turns out the types of gaps you can get with those gauge blocks is something on the order of a tenth of an inch, a tenth of a mil, or 1/10,000th of an inch. These things have very good finish, and so you can really get them on there closely. And in fact, if I had any chalk dust, sometimes I can't ever get those together because I get chalk dust on them. And chalk dust will be enough to keep it apart that I can't get those things to adhere. Remember, they got us ring together with 50 millionths of an inch accuracy, which is something like a less than 1/10, less than 1/10,000th of an inch. It's about 1/20th, or 1/20,000th of an inch. 50 millionths is 1/20,000th of an inch. So that in order to stack those things up, they have to have a very, very tight tolerance on that surface finish. So in any case, I end up with this Stefan equation, which is a nice thing for me to give you homework problems on. But actually up here on the Stefan equation, it gives you some examples. If the force in this force time product is 14 psi, and the viscosity of the material is 1 gram per centimeter second, and A squared is, there's H1, H2. You must tell me what A is. Oh, X is 1 centimeter. So A is X, in this case, 1 centimeter radius. And you go through this. The time for separation with these two spacings, or H2 initial and final spacing, is 20 milliseconds. If I go through some different things here, and if I get this thing down to viscosity 10 times greater and a distance of the thing of 10 centimeters across, a lot larger area, and I get the final spacing down to 1,000th of a centimeter, it takes 20,000 seconds for the viscosity to allow the thing to separate. Okay, it's just a question of viscosity. So what's the point of the Stefan equation? Well, the Stefan equation tells you several things, and putting some typical numbers in the Stefan equation helps you understand a few things. If I was, if I want to put it on the wall, I just try to squeeze harder. Now, a better thing would have been to clean the wall to get rid of all the grease and oil and everything, to get a better value of surface tension to begin with, to get more type 1 adhesive bonding to hold the thing together, force on there. But if I want to look at the kinetics of this thing falling off with the Stefan equation, I want to get a thin joint, but I also want to have it stay on. I'd like to have a high viscosity, right? Now, how do you get a high viscosity in something? Well, there's a Stefan equation. How do I change the viscosity of something? You can heat it up and you melt it. Well, particularly if you melt it, if you go from a solid to liquid, does anybody have an idea of what the typical viscosities of things are? The viscosity of water is about 1 centipoise. Yeah, it's about 1 centipoise. Okay? A poise is a measure of viscosity. And water is about 1/100th of a poise. A typical solid, anybody have an idea of what the viscosity, and viscosity is just the resistance to shear, right? Shear flow, right? A solid has a viscosity of somewhere on the order of 10 to the 10th, 10 to the 15th. Professor Orawan, who was one of the founders of dislocations, once estimated the highest viscosity ever measured was 10 to the 22nd. And it happened to be the Finnish coastline. And he had to look at geological data in order to get his time constants. When you start getting to viscosities of 10 to the 22nd, you can't measure them in your lifetime. You have to measure them in millions of years. okay, to measure the flow of something like that. Well, I'm not sure if that really is the true viscosity of the finished coastline. I mean, he was looking at some shear force moving the coastline. But basically, I can go from a liquid, like water, that flows reasonably well. You know, there are some liquids that flow better than that. There's viscosity of air, which is like thousandths of a centipoise, or slightly less than that. Okay, but I can go from 1/100th of a centipoise, or I can go from 1 centipoise, 1/100th of a poise, up to 10 to the 15th poise without any great difficulty. 17 orders of magnitude. So if I have a liquid as an adhesive, and this is just lubricant to keep those things from rusting, right? So it's just a light, it's kind of like WD-40, maybe a little heavier than WD-40, but it's not much different than WD-40. If I have a liquid like that, I can make the joint very quickly in milliseconds, potentially, if it has a low enough viscosity. But if I do something to harden it after I put it in between the two surfaces, and I go up by 10 orders of magnitude, something that would have lasted for 2 seconds or 20 milliseconds, if I go up by 10 orders of magnitude, it lasts for 10 to the 8th seconds, right? If it's down at 10 to the minus 2 seconds, 10 milliseconds, 10 to the minus 2 seconds. If I go up by 10 orders of magnitude in viscosity, then I'm going to get 10 to the 8th seconds. How long is 10 to the 8th seconds? It's about a year. If I go up 12 orders of magnitude, I get 100 years, right? So the thing's bonded together. The important term in the Stefan equation, there are two important terms. One is this final thickness, and the other, which dominates a lot more than the final thickness, this is 1 over h squared. So if I make the thing 10 times thinner, I get 100 times the force time product. But if I solidify the adhesive and go from a liquid adhesive to a solid adhesive, I can get 10 orders of magnitude, not 2 orders of magnitude. Yep.
The Drano was taken 0.1 centimeter, or it's just like by chance that all the 3 examples is 0.1?
Oh, is the initial height?
Yes.
Oh, he just took that as an initial height because that's the typical film thickness of an adhesive, 0.004 of an inch. I mean, that's just his examples. Okay. You'll get a chance in your homework to plug in some numbers, okay, to see how. But it turns out I'm sorry, he's talking about squeezing the thing. His H1 is his initial height, H2 is his final height. He's talking about squeezing the thing between two pieces. In some cases, we're talking about squeezing when we form the adhesive joint. In other cases, we're talking about pulling it apart, okay? You can use the same equation for either one. If you go back and look at, it's just, where did I put it? It's just the flow of a viscous liquid spreading out between two plates. Well, it can be a viscous liquid flowing in as opposed to flowing out in terms of the dynamics of the shear, okay? It doesn't really care, you just change the sign of things. In his case, in his examples, he was talking about how long it takes to squeeze it down to a thinner piece, but in pulling it apart, you can just assume that if once it gets to a certain thickness, it'll just kind of let go, okay? But the real point here is, in order to get a strong bond with type 1 adhesive bonding, I really need to do something to change that viscosity, and we're going to talk about that in a second. But in the meantime, we can talk about what I call type 2 adhesive bonding, and type 2 adhesive bonding is nothing more than mechanical interlocking. Anybody know what this is a picture of? It's a scanning electron microscope that's been colorized. Velcro. Okay, you make these little loops out of nylon, and then you cut them so they make hooks. And then, I'm sorry, this is the nylon up here, and the it's a different plastic for the. Let's see if it tells me. Anyway, this is nylon up here, a little nylon fabric. It's the fuzzy, the soft, fuzzy part of the Velcro, and then the hooks. This is just this is nylon, and this is either polyethylene or polypropylene, I think, typically. But anyway, different plastics. But basically, this is just mechanical interlocking. You can see the hooks grab onto the smaller nylon. so far as that goes. It turns out a lot of what we deal with is mechanical interlocking. And in fact, if I had to pick which one was dominant, I would say mechanical interlocking as a type of adhesive bonding is probably more important than type 1 adhesive bonding. But we can go through that and think of things. But let's say if I put bricks and mortar together, that tends to be mechanical interlocking, right? I got rough bricks and the mortar kind of gets down in there. There has to be some wetting, and it's actually a combination of the two, type 1 and type 2. But many times if I roughen up a surface, and I forgot to bring it today, to show you what happens with aluminum. In order to get good adhesive joints in aluminum, which we like to do for aircraft and things, we actually anodize the surface, so we get a very rough surface when we anodize. And we also do some other things on steel and whatnot to roughen the surface, and I'll bring some of those things tomorrow. But let's talk about there's three principal ways to go back and talk about changing this viscosity to harden up an adhesive. Anybody know what they are? See if you read chapter 16. Barry? Oh, you did? Yeah, okay. It turns out I call that solvent removal. So I could have made a liquid by dissolving a solvent into it, and if I dry off the solvent, the stuff hardens up again. What's a good example? Cement. Well, cement actually is the third one on my list. Cement is actually a chemical reaction, so I just gave you the third one. We can talk about, and I'll put, you're talking Portland cement, right? Yeah, mortar. Okay, Portland cement. Okay, calcium burnt lime, calcium oxide. You actually mix it with water and it forms calcium hydroxide, and it actually forms crystal. There actually is, and there's a heated reaction. I had a situation once where some people installed some polyethylene tubes for cooling tubes in a hockey rink, and they poured concrete over these tubes, and then they were going to put the water on top of the concrete. And they ended up with a sprinkler system because it turns out the polyethylene would only take about 170 degrees Fahrenheit, and Portland cement can actually heat up. They did this on a hot day in July, and so the tube was probably already, black tube in the hot sun was probably already at 130 or something, and the Portland cement was probably also warm, and when they poured it on there, they actually got temperature sufficient to melt the plastic. Okay, and so the joints failed and everything, and so all you had to do was go in there and jackhammer everything out and start all over again, right? But they didn't know why everything failed. But it turns out cement will actually heat up, and if you're casting something like the Hoover Dam or something that's huge, you actually have to do some things to put cooling channels and stuff in there to extract the heat, because if you make the thing too big, it'll take forever for the heat to just diffuse out if you go through typical diffusivities. Anyway, solvent removal. How about a postage stamp? Yeah, well, actually you're right. We don't use that kind. But the old type, or an envelope. How about an envelope? Where you lick it, that's the solvent. And then where does the liquid go? Well, it evaporates, but actually it wicks away into the paper because the paper is porous. So it takes a little bit longer actually to completely evaporate, but the porous paper actually wicks it away. If you try to use a solvent type of glue on something like glass, it won't work because the solvent has nowhere to go. It's stuck between the layers of glass, and the glass is not porous. If you want to use solvent removal, you better have something at here end that is porous enough to absorb the solvent. And so it actually initially will usually be wicking away. Elmer's glue, okay, or it's basically just got water in it. and it dries up. Airplane glue, right? It's got something, and you sniff it, right? You got something that dissolves part of the plastic, and when it goes away, you're left with plastic afterwards. The second one is solidification, which someone already mentioned. You heat it up, and you got plenty of hot melts, hot melt adhesives, glue guns, you know, a little electric gun. You put this piece of plastic in the gun, and you heat it up, and it melts, and you squirt it out. And if it's fluid enough, when it squirts out, you make a nice thin joint. And if it gets too, and then as it cools down, it will solidify. Asphalt on the roads, okay. You heat it up. You've seen them. They put it down hot, right? They put it down hot, and it cools, and it sticks all the rocks together in the road. Chemical reaction: Portland cement, epoxy, superglue. Turns out, superglue. Anybody know what superglue is? It's a, well, you know what it is, but do you know what the chemical compound is? It's called a cyanoacrylate, and it turns out it was found by serendipity. The serendipity in this case was the guy was studying. In fact, it might be in here. He was studying these cyanoacrylates, and it may tell the story in here. I don't remember, but I think he got some on his fingers or something and glued his fingers together, and decided there was something interesting going on here. Cyanoacrylates, 569. They're unique in their ability to polymerize rapidly at room temperature without the addition of a catalyst. Okay. First commercial was Eastman 910, introduced in 1958. And I guess this book doesn't give you the history of this guy doing it. I got another book downstairs, and I don't remember all the details. But basically, it was an accident, and he basically was sticking things together that he didn't want to. You don't have to, it does polymerize, but you don't have to have a catalyst. And the reason is because the catalyst happens to be OH radicals, hydroxyl radicals. And the reason it glues your skin together is your skin is slightly basic. If you measure the pH of your skin, it's kind of like 8 or 9, slightly basic. So it bonds skin together really well. It doesn't bond certain woods together very well, because certain woods are slightly acidic. And in fact, if you want to use superglue glue on wood, you ought to paint it with Drano first, right? Because Drano is a base. Drano is just basically sodium hydroxide. And because it's the hydroxyl ion that acts as the catalyst for the polymerization. And so it says it doesn't need a catalyst. It does need a catalyst. It's just hydroxyl ions are around wherever moisture is. And so in the case of superglue, the reason people consider a superglue a superglue is because it sort of uses the moisture that's present there anyway. And so people think it sticks really well because they haven't bothered to clean the surface. They use some other adhesive, and they're basically trying to bond to a moist surface. In this case, the superglue kind of consumes some of the moisture that's there on the surface, and it's sort of cleaning as it, as it uses up the catalyst, so far as that goes. So we think it bonds really well, but basically all it does is harden up in the presence of a catalyst. Anybody know what Loctite is? Loctite, this little adhesive that you put down between screws. You coat the screws with it. It's nice and fluid, and you screw the screw in, and it hardens up. Do you know what causes the Loctite to harden up? It's not solidification because it's room temperature. There's no change in temperature. And it's not, no, it's not friction. It's solvent. It's not solvent removal because you're stuck down in between the threads. It turns out it's a chemical reaction, but in this case, the chemical reaction is because it's an anaerobic adhesive or anaerobic polymerization, which means in the absence of oxygen, it will polymerize. And if you look carefully at these little Loctite or fastener adhesives, somewhere on their cap or somewhere there'll be a little bitty hole to allow the air in. Because if they didn't, it would harden up in the tube or in the can or whatever. Okay? If you take the oxygen away, it hardens up. So it's an anaerobic adhesive. So that's what Loctite, which is a billion-dollar-a-year corporation now, bases its growth and everything on the fact that they developed something that polymerized in the absence of oxygen, and that's exactly what you got down in the threads. Okay, so people get pretty clever about doing these things. What are some of my other examples here? We talk about airplane glue, cyanoacrylates, anaerobics, epoxies. Epoxies, you obviously know, you have to put the catalyst together with the base, and you mix the two of them together, and so that's a polymerization reaction. Okay, what else do we want to talk about on these things? In fact, let me give you an example of mechanical interlocking, since we got to tell a story every day, right? At least one story. This is a piece of Millennium cookware by Faberware. And actually, there's a good example of cold welding here. This has got an aluminum base to a stainless steel cooking pot. You want the aluminum base because it distributes the heat well. And that's a pretty hefty piece of aluminum there. That's not quite a quarter of an inch thick. If I remember correctly, I've been in the plant in Brooklyn where they make these things, and it's kind of an interesting plant. It's about 4 city blocks, and it's kind of in an area of town that's sort of like a battle zone. And I had to walk around all 8 city blocks to finally find the entrance. There were no windows. I mean, it's just you get inside and it's okay, but on the outside, and it was after a snowstorm. But anyway, so I was crawling over the snow on the sidewalks and wondering if I was going to get mugged in the next block. Anyway, so anyway, to make this cold weld, they basically just take the pot, which has already been formed, they put it over a die, they take a piece of heated aluminum, and they put it on here, and they have a great big press that comes down, wham, okay, with, I can't remember how many tons of force, but it's like a 1,000-ton press to hit this thing, and it just forges this thing on there. And it turns out, I always wondered, well, how do I get something like this, and I heat it up, and it doesn't just expand and cause problems? Well, it turns out there is a slight curvature down. But the real reason is they actually only get about 10% bonded area. They're not getting a lot of shear when they do this. They get some shear because they coin this. I mean, they hit this thing really hard so far as that goes. In fact, that's how I'm pretty sure that's when they emboss this, the stuff in the metal. But if you actually were to take this thing apart, it actually is probably only 10% bonded. You got so much area, you don't really have to have a great bond here. And it turns out if it's not 100% bonded, you can get a little thermal expansion without the thing delaminating on you or starting cracks. But there is a different problem why they came to me on this. But this is, I don't know, this is a $100 pot or a $150 pot if you got to go buy it, because it's got a Teflon coating in here. Millennium cookware has got this very adherent Teflon coating. And it turns out the way they make it is they plasma spray stainless steel powder in here. So they end up with a porous surface on the inside. And plasma sprayed stainless steel is essentially welded as a porous, spongy layer. And then they impregnate that porous powder with the Teflon. So this is mechanical interlocking big time, right? The stuff is just impregnated in this spongy, it's a composite. And it's very hard to get that off, so it lasts really well. Well, the reason they came to me is they were shipping these things across the ocean, and when they would get to the other side of the ocean, they would have cracks in them. See the crack? Okay. And they came and they said, we know we didn't ship them with cracks. And how did they end up with cracks when they got across the ocean? Is it some sort of corrosion on the ocean voyage and stuff? And I said, no, but it's got to be related to hydrogen. And they said, well, this is a 300 series stainless steel. You know, it shouldn't be susceptible to hydrogen embrittlement. But hydrogen cracking is often called delayed cracking. And at the time, I didn't know that they were plasma spraying the inside. But it turns out the plasma spray process is where the hydrogen got into the metal. And then, in order to get hydrogen cracking, you have to have a source of hydrogen. Well, that's from the plasma spraying operation. There's moisture in the air and the gas and everything, and it would get into the metal because it breaks down the moisture in the air. But then you have to have a source of stress. What's the source of stress here? Well, the whole thing was formed from a sheet and into a deep draw here, and that creates some residual stresses, particularly up here. However, that's not the real reason, because the 300 series stainless steel is face-centered cubic, which is generally fairly immune to hydrogen embrittlement. However, what I did, they were sitting down in my office around the table. I went and I got a magnet, and I said, yeah, it's stainless steel. It's only slightly magnetic down here. But if you get up here, it's really magnetic. And you can the reason it's got tabs on here, we ended up having a student go through and measure the liftoff force. We have a little gauge down there that they actually use to measure hydrogen, the susceptibility of hydrogen in weld, or not susceptibility of hydrogen, the amount of ferrite. It turns out a 304 stainless steel, if you do a lot of mechanical work on it, will transform to martensite. And martensite is ferromagnetic. And martensite is susceptible to hydrogen embrittlement. And those cracks start at the top where the stresses are highest. The hydrogen's throughout the whole thing because it's plasma sprayed throughout the whole thing, so the hydrogen is probably fairly uniform. But the maximum amount of work is up where the thing got rolled, the maximum amount of deformation is where it got stretched at the top. And so you have the maximum residual stress, the maximum amount of martensite as you go up there, and you can tell the amount of martensite by running the magnet across there. In fact, what we used on that is something called a magnet gauge, which is what welders use on stainless steel to measure the amount of ferrite in their stainless steel weld. You want about 5 or 10% ferrite in your stainless steel weld to avoid some hot cracking problems. And so they use a little magnet gauge, and it's just a little balance with a magnet on it. And you measure a certain amount of liftoff force. Well, we measured the liftoff force, but you can measure the liftoff force not quantitatively, but qualitatively. And so their problem was plasma spraying got hydrogen in there, residual stresses are present in the lip of that thing, and the metal had transformed to martensite. So that was why it was cracking, and the solution is, well, you got to bake these things out to get the hydrogen out before you put the Teflon on and before you ship them. Typically, if you get hydrogen into a metal, it takes, depending on the hardness of the metal, it takes a certain amount of time. It's delayed cracking. There's a new ASTM specification that basically says if you electroplate chromium, let's say, on a part to give it a hardened steel part to give it corrosion resistance, that you must put it into a furnace at 375 degrees Fahrenheit within 1 to 4 hours. If you don't do that, you're liable to get hydrogen cracking. For example, the U.S. Navy in building submarines, they will not do their magnetic particle testing on their welds until 1 week has passed since the welding, because they want to give the hydrogen time to diffuse out, or if any hydrogen cracks are going to form, they want to find out about them. If you went and tested for cracking within 1 to 4 hours after making a weld on a heavy piece of steel, may not be a crack there. But the next day, the whole thing may be cracked because it takes time for the crack to develop. In this case, they loaded them on the ship, and when they took them off the ship, they were cracked because of delayed cracking.
They find the ones being distributed in the U.S. also being cracked after they purchased.
I don't know. That's an interesting question. They came to me because they first noticed a bunch of them cracked. I mean, I suspected. Now, the other possibility is maybe the ship was going through a cold area or something and had more time. I never asked them that question, but I mean, they came to me because they had been noticed the whole shipment had been cracked. And maybe they'd just been plasma spraying on a particularly humid day. Maybe the air conditioning was off in the plant or whatever. I don't know. It turns out in a naval shipyard, if you go down here, the Navy has a specification for how much humidity you can have at the shipyard to do welding. And it turns out that you exceed that level 75% of the time. They don't bother to stop welding. They do have a specification that you shall not weld above such and such a level of humidity. They just ignore the specification. So anyway, okay, I think that story took us to the end of the day. Okay, see you tomorrow.